Hello everyone. So today we are going to talk about DOE, which stands for Design of Experiments. And using DOE, you can basically do empirical modeling. That will tell you variable effects and the interactions between them. So the easiest way to tell what DOE is really, it is a modeling scheme. For example, if you were an engineer in Micron, right, you will want to, say, grow crystals on a substrate. Let's say, here's a substrate. There you go. And you are growing crystals on it. Let's say, here's a crystal. Let's make it look a little different. Okay, so here's your crystal. Okay, and let's say you are in a chamber. Okay, and you have two things, the chamber temperature, okay, and the gas pressure. Okay. So you can imagine that the crystal growth is a very complex system, and you don't necessarily have new equations that you can predict what's going on. So therefore, you're going to have to rely on experimental measurements. And to do that, you basically measure temperature and pressure. Or measure the crystal growth under different pressures and temperatures, and based on that, you will come up with a physical or empirical model that will predict how these two variables are affecting crystal growth and how can you optimize these variables to achieve the growth that you like. Okay, so for today's purposes, we are going to talk two levels and two-factor DOE. Okay, so that means that you're going to have two levels for each level for, say, temperature and pressure, right? So you have temperature, pressure, and then you're going to have a minus, which is minimum, and we are going to have a plus, and you're going to have the same thing for the pressure as well. And you can imagine that this system is basically a square. It's a two-dimensional system, right? So you have four corners, right? Which is the corners that you're going to measure with your experiment. So let's say make an origin. Right, and let's say this is your temperature, this is your pressure, right, and this is your 0, 0, and you can call them, say, AB, like a coordinate system, right? You can call them, let's say, temperature and pressure. Right, and therefore, for this corner, right, you're going to have your temperature is going to be plus, and your pressure is going to be minus. In here, your pressure and temperature are going to be plus, plus. This will be minus, minus, and this will be minus, plus. Okay, and based on these measurements and the average of all of them, which is 0, 0 point, right, then you can write a basically an equation say y, which is the response of the system, right, is as the alpha 0, which is the average, right, plus a times alpha 1 plus b times alpha 2 plus ab times alpha 3, and these alpha 1, alpha 2, and alpha 3 values are extracted from your 4 experiments. And based on this equation, then you can predict anything that's going to happen within the system between these A and B values that you have measured. So within the measurement system that you'll be able to predict everything that's going to happen. And these plus and minus values, right, minimums or maximums, going to have to be chosen very carefully, meaning that you want them to be as spread as possible. In other words, you want minuses to be the minimum possible value that it will go, right? And the plus is going to be the maximum possible value that you can go. These plus and minuses are usually determined by things like safety. Like, for example, we don't want the temperature in this chamber more than 800 kelvins, right? That might be a safety issue. Physical limits. Right, basically the temperature cannot be less than 500, more than 800, depending on the specs of the oven that you use or the chamber that you use or the budgets, right? And that might not be feasible to run it at certain temperatures and pressures, because then it will be too expensive to run. So with that, let's do an example of how you can actually accomplish DOE. For this example, we are looking at 2 factors, right? Let's say 2 factors, and let's say the factor 1, let's call it A, is going to be spark plug gap. Okay, and your factor B is going to be spark plug wire resistance. Okay, so, and you want to measure the outcome variable, right, as the horsepower of the engine. Okay, and for that, since you are doing 2 levels, right, so each going to have a minus and a plus value, that means that it will be 2 over 2, and that's going to be 4 experiments. Okay. So let's say you have done the 2 experiments, right? And they are given as, let's shorten them, spark gap, right? And slash spark wire resistance. Okay. So we have a table. This way we have the spark gap in inches. It says 0.035 and 0.065 inch and inch. And in this side you had the wire resistance, and you had 10 and 40 ohms. Okay, and you can already say that this is minus, this is plus, and this is minus, this is plus, and that means that you have done 1, 2, 3, 4 experiments, right? Let's make the table separated. Okay. Okay, and as a result of these experiments, you got 165, 155, 198, and 180. Okay, so now this is a standard sort of DOE experiment that you would do, and you get 4 different measurements. And now the goal here is to find these alpha 0, alpha 1, alpha 2, and alpha 3. These are also effect sizes for each. And to do that, you usually do a standard table. These table formats are given in engineering handbooks. Therefore, you don't have to know what this is, but you can just go to engineering handbook and find. So to do that, we'll do a run number, right? So we'll have 4 different runs. We have A, we have B, then we have A times B, as well as the response, which is Y. Okay, so runs are 1, 2, 3, and 4. Our A's are going to be defined by minimums and maximums, so I will make this as plus, minus, plus, minus, plus, and this will be minus, minus, plus, plus, and A times B is what it is, so it will be minus times minus is going to be plus, plus times minus is going to be minus, minus times plus will be minus, and plus plus will be plus. And these are the runs that we have done, and you can imagine that these are the corners that you have made in the previous page. So it will be 165, 198, 155, and 180. Okay. What we will do is to calculate the effects of AB and AB interaction. Let's start with A. I am going to write this in blue. So define the effect of A as EA here. EA. And that's defined as when all the sum of all the values when A was plus minus sum of all the values when the A was minus divided by 2. So if you were to define the A plus, okay, we're going to have to go back to our table and see when the A was plus, right? So you can see that our A was plus in run number 2 and run number 4. So that means that it is going to be 198 plus 180. Okay, and that will be 378. And our A minus is going to be 165 plus 155, right? And that's going to be 320. Okay, so from there, then you can write the effect of A is going to be 378 minus 320 divided by 2, and that's going to be 29. Let's do the same thing for effect of B right now. I'm going to write this in green here. So the effect of B is going to be B plus minus B minus divided by 2, and B plus is going to be all the cases when the B was plus, right? So that's going to be say number 3 here, right? And also number 4. And that means that it's going to be 155 plus 180, and B minus is going to be the cases when the B was minus, right? So you can readily say that's going to be 165 plus 198. And if I write the effect of B, right, it's going to be B plus minus B minus divided by 2, and that's going to give me minus 14. Okay, so I can do the same thing for A and B, I'm running out of space here. So the effects are -29, okay, minus 14, minus 14, and if I were to do the same thing for AB, I will find it a minus 4. Okay, so and the Y is the average of everything, so that will be 174.5, and that's the average. Okay, and with that I can calculate the system response. Let's do the summary. Our two factors were A and B, and our two levels were minimum, minus, or maximum, plus. Okay, and using that we have accomplished 4 experiments. Okay, using those 4 experiments, we have calculated the effects for A, effects for B, and then the interaction of A and B. We have found that the effect of A was 29, effect of B was minus 14, and then the effect of AB was minus 4. So the first thing that I can do here is, the first conclusion is to compare effects. Okay, and when I compare the effects, that I could have said that the effect of A was the larger than effect of B, and that was also bigger than the interaction. So now I can say this, compare the effects, and next week when we are doing our experiments, we can do a t-test to find whether effects are significant, right? So I can do a t-test between all the A minuses versus all the A pluses versus all the A minuses, and if the effects is larger than a certain t value, right, the t critical value, then I can say if this is significant or not, and I can do the same thing for effect of B and effect of AB, and I would say the A, right, in this case was, I guess, Y resistance was able to change the system response by 29, and that was a significant effect or not. And I can make these type of conclusions using DOE. Now we have done with this summary, let's get back to understanding how to model the system using empirical modeling. Response of the system Y is going to be alpha 0 plus A alpha 1 plus B alpha 2 and plus AB alpha 3. So alpha 0 is the average. Okay. Alpha 1 is the effect of A divided by 2. Alpha 2 is the effect of B divided by 2. And alpha 3 is the effect of AB divided by 2. So in that case, the total response can be defined as, right, alpha 0 plus A times EA over 2 plus B times EA over 2 and plus AB times EAB over 2. Okay, so in here, the A and B are the effects, and EA and EB are effects, and the AB are the scaling factors. Okay, so let's go back to our visualization, right, for a 2x2 model. Here's the origin of all the measurements, right? That's going to be 174.5. And you have your four corners, right? Is the square. You're gonna have your plus corner. That's going to get you 180. You're gonna have minus plus corner. That's gonna get you 155. You're gonna have your plus minus corner. That's gonna get 198. And you're gonna have your minus corner. That's gonna get you 165. So these four corners are your experiments that you've done, and then the origin is the mean of all the experiments, right? So that's your origin point. And the equation y here is going to predict how your system behaves in between these A and B values. So basically, in other words, if your A and B values are smaller than 1, right? I put it absolute because it could be plus minus 1. That means that you predict inside, right? So let me see if I can change the color. So shown by red, this will get you to predict inside, right? And if your A and B values are larger than 1, right, you're going to predict outside, meaning that you can predict outside of your box. However, this is usually not done too much because sometimes your system may behave differently outside of the box than inside. So the idea here is to select your boundaries accordingly. So that means that you select your minimum and maximum values so that every possible value that you want to do is contained within the box, and then you use A and B values that are smaller than 1 to predict the response inside the box. If you like to do a further optimization in the future, right, you usually select your response and select the smaller box within your box to do a further optimization to sort of get to a different values. We will do these in the other class, so you shouldn't be worried about it now. And just do a sort of example of how this y equation, right, can predict the corners. Let's, what did I do? Let's do the next page, and let's try to predict our corners. Okay, so let me change the color back. So your y1, right? Let's say that's the minus corner, right? Is going to be 174.5 minus 14.5 plus 7 minus 2, and that's going to be 165. So that means that if I used minus 1 for A and minus 1 for B, I predict 165, which is my minus corner. If I do the same thing for plus minus corner, right, you will see that it's going to give me, so that means that the my A was plus 1 and my B was minus 1. So that will give me 174.5 plus 14.5 plus 7 and plus 2, and that's going to give me 198, and that was my minus plus corner. And similarly, if you do y3, which is minus plus, you'll get 155, and if you do y4, which is plus, you can get 180. Okay, so this is pretty much the DOE that basically lets you build a model that given by y here, right? Let's write it again. So the given by y here, and that y is then used to predict the system response and even optimize the system response, because you can find a solver that will maximizes the y based on these A and B parameters. And we're going to have a YouTube video posted about this and how to do that in Excel. Okay, now we learned how to do this by hand, right? That means that the we can use these tables, standardized tables, to figure out what the effects of variables and the system response is, right? You can also do this in a matrix form. That means that if I define my response y times a times x, right? And in here, my y is the response matrix. Okay, and my A is the design matrix. Okay, and my X is the factor effects. Right, so that means these are your E's. Okay, so we want to solve for X, right? Because we, if I were to rewrite my equation here, alpha 0 plus A times alpha 1 plus B times alpha 2 plus AB times alpha 3, what we are trying to solve here is my alpha 1, alpha 2, alpha 3, as well as my alpha 0. So that's the factor effects, right? Maybe I can write this also as, delete this. Oh, I delete the whole thing. It could be E's, right? Or it could be called as alphas, right? So it could be either way. So if I were to use the table format, right, that I've done before, I know that the alpha 0 is the average, right? I know that the alpha 1 is the effect of A divided by 2. I know that the alpha 2 is the effect of B divided by 2, etc. But if I were to do this in a matrix form, right, then I can solve for these constants, x values, right, using the transpose of the inverse of A times y. Okay, so now I can define my matrices. Let's define x, right? X is defined as a vector alpha 0, alpha 1, alpha 2, and alpha 3. Okay, similarly, your system responses are again y1, y2, y3, and y4. Okay, and your A is simply the table that we have used, and your first set of values is going to be your identity matrix, plus 1, plus 1, plus 1, and plus 1. Right, and that will be pulling out your average when we do the matrix multiplication. Then you can also do your values for A, row that goes to A, right? That's the same thing that we've done in our table. That'll be minus 1, plus 1, minus 1, and plus 1. We can do the same thing for B, which was minus 1, minus 1, plus 1, plus 1. And if you will, we can do the same thing for AB, right? That will be plus 1, minus 1, minus 1, and plus 1. Okay. So with this, so I have done is the A matrix. Okay, let's try to write down the inverse of the A matrix. Okay, A minus 1. Okay, and let's do that. And when I invert this matrix, I can rewrite this is like that: 0.25, 0.25, 0.25, 0.25. And my second column is going to become my second row, right? That will be minus 0.25, plus 0.25, minus 0.25, and plus 0.25. And my third column is going to become my third row, so that will be minus 0.25, minus 0.25, plus 0.25, and plus 0.25. And my last column is going to become my last row, so that will be plus 25, minus 0.25, minus 0.25, and minus 0.25. Just for completeness, let's write the pluses here so that there is no confusion. Okay, and now if I were to write then my matrix that I'm trying to solve for, alpha 0, alpha 1, alpha 2, and alpha 3, right, is equal to A minus 1. I'm not going to rewrite A minus 1. You already had it, right? And times my response matrix, that will be 165, 198, 155, and 180. Okay, and if I were to do this, then the alpha 0, right, is going to be I'm just going to write it from the previous definition of a minus 1. It will be 165 times plus 0.25, okay, plus 198, okay, times plus 0.25, okay, plus 155 times plus 0.25 and 180 times plus 0.25, and that will be equal to 174.5. So going back to the previous page, you can see that the this was first row multiplied by the first column, right, of y, and that's going to give me
alpha 0. If I were to solve for alpha 1,
I'm gonna go in and then now take this second row of my a minus 1 and again multiply it by the y, and that's going to get me alpha 1. And if I do this, you will find that the alpha 1 is going to be equal to effect of a divided by 2, right? That will be then 29 divided by 2, so that will be 14.5. Alpha 2 is going to be effect of b divided by 2, that will be then minus 7. And alpha 3 is going to be effect of AB divided by 2, and that's going to be minus 2. And you doing that, you can do this in the matrix form. And after this lecture, I will show you how to do this in Excel. Okay. And this is called a coded DOE. That means that your A matrix, right, has the values that you coded to either +1 or -1, okay? So in an uncoded DOE, you will have the ability to use the real values, and that means that I can use the real values of 10, 40 for the Y resistance, and for the gap values I can use 0.035 and 0.065, right? And now the pros of this method really is to be able to use real values, right? So use real values. Right, for example, if I wanted to go and predict the case where A was 30, right, and B was 0.04, I would be able to predict it using real values of A and B. So if I were to write the system response here, that would have been alpha 0 plus alpha 1A plus alpha 2b plus alpha 3ab, and I would have used an average value. I would have used 30 for A, 0.04 for B, and the multiplication of the two for the interaction, and I would have got a system response. And that's pretty easy to do because it's intuitive. I'm using real values. If I were to use a coded view, as you can imagine, I would have to use different values for A. So the A in this case would have been something like 0.5, and that could be maybe close to 0.5. I'm not so sure, but close to those values. And that's not very intuitive. The cons, however, is that the effects are not real. Effect sizes are not real, right? So, and I will show you this in Excel, the differences in effect sizes. But if you go back to the earlier in the lecture, we could have said there are effects of A, effects of B, and effects of AB, which is the interaction between the two, right? And I knew that this was 29, this was minus 14, and this was minus 7. I could have made the observation that that the effect of A was larger than effect of B, and that was larger than the effect of AB interaction. And I would have said the A was the most important factor, changes the system the most, and B is the second, and then the interaction was a little bit less. I'm sorry. Effect of AB was not minus 7. It was minus 4. Correcting that. So with this type of coded DOE, I would be able to say the difference between the effects, but in a coded DOE, these effect sizes will not be reflective of their influence on the system response. Therefore, I cannot do these comparisons in a coded view. And that's one of the disadvantages of using coded view, uncoded view. I'm sorry. So in other words, I would in an uncoded view, I would be able to use real values of A and B to predict the system response. However, I cannot compare the effect sizes to each other. To do that, we'll have to do an coded DOE. Let's do the summary. Today we have done 2 levels, right? And 2-factor DOE, right? Our 2 factors were A and B, and our 2 levels were minimum, minus, or maximum, plus, okay? And using that, we have accomplished 4 experiments. Okay, using those 4 experiments, we have calculated the effects for A, effects for B, and then the interaction of A and B. We have found that the effect of A was 29, effect of B was minus 14, and then the effect of AB was minus 4. So the first thing that I can do here is, the first conclusion is to compare effects. Okay, and when I compare the effects, that I could have said that the effect of A was the larger than effect of B, and that was also bigger than the interaction. So now I can say this, compare the effects, and next week when we are doing our experiments, we can do a t-test to find whether effects are significant, right? So I can do a t-test between all the A minuses versus all the A pluses versus all the A minuses, and if the effects is larger than a certain t value, right, the t critical value, then I can say if this is significant or not, and I can do the same thing for effect of B and effect of AB, and I would say the A, right, in this case was, I guess, wire resistance was able to change the system response by 29, and that was a significant effect or not. and I can make these type of conclusions using DOE, and different than in normal tests, right? Just changing A or B, I can now say whether the interaction was also significant or not. So doing that, I can do the first thing. So my first conclusion that I can compare the effects and I can test whether these effects are significant or not significant. Okay. So then I would be able to do, so let's say this is number one, and number two, I can model the system, right? And I can model the system as the alpha 0, which is the average, right? Plus the A times effect of A divided by 2 plus B times effect of B divided by 2 divided by 2 plus AB times effect of AB divided by 2.
We can also use statistical tests to understand whether the effects of A, B, and AB were significant or not using t-tests or other type of tests. This week we are not going to cover them, but in the class on April 6th or the week of April 6th, we will cover those topics.